Hello and welcome to this new video where we're discussing mathematics and physics on the board. Today what we are going to look at is the law of similitude in fluid dynamics. This law is very important because it allows to essentially model the fluid dynamics of a particular system that can be incredibly large, like a cruise boat, like a gigantic ship, like the Titanic, an airplane, whatever, and basically to model that and to have an equivalent fluid dynamics phenomena appearing in the system, but basically on a scaled down system with different kind of fluids in there, etc. And so this is what we are going to do today, and it involves the combination of Buckingham pi theorem and Navier-Stokes equations. Right, so let's put a bit of context here. So let's summarize this Buckingham pi theorem that we had discussed in some previous video. Essentially what it states is that if you've got some physical problem, and these physical problems involves m different variables and parameters. Okay, so like everything, right? Everything that you need to account for is going to be in that particular equation. And you have as well an independent dimensions in your system. Then you can actually create an equation that contains m minus n different variables that are dimensionless, and these variables are called pi, so that's why actually it's called Buckingham pi theorem. There's nothing to do with pi, it's just a name that were given to the variables. So we use that in a simple case of a pendulum. That's fine. And then here we counted kind of explicitly the variables, etc. We're not going to do that in that particular fashion here. What we are going to do instead is basically try to describe a very complex physical system, which is that of fluid dynamics with a flow field and all that, around a particular obstacle, and then we are going to look at how we can express the equation in terms of dimensionless quantity, and then we can try to see what kind of gain we've had compared to what we started with. Okay, so this is this Buckingham pi theorem. So that's it. Now that's the most complicated part I'm talking about. So the Navier-Stokes equation turns out actually to be a relatively simple equation of fluid dynamics. There are many more complicated ones that are even more nonlinear. So here there is a nonlinear term here in V, but there could be more complicated nonlinear terms. You could have explosive terms, so like some aspects associated to like the Burger's equation for sort of explosion, like compressibility is added to it, and so on and so forth. So it's actually a quite simple one. However, with this, you can already get like turbulence and plenty of stuff, right? So it's a relatively accurate equation, but simple in terms of what can be out there in the kind of models we can find in fluid dynamics. Anyway, so it reads like this. Now, I'm not sure I want to read out loud what these terms are, but essentially, this is the whole term here is what is called the material derivative or convective derivative. What it does is it tells you how the velocity is actually changing with time here, but explicitly with time. So it means that if you stop at one particular point, you're going to see how the velocity varies, if it varies at all. Then here this term is telling you how velocity is transported by the existing flow, okay? So you see that even if your velocity field does not depend on time at a given point, you may still be transported by the flow itself. So that's what this term does. Here you have the influence of pressure. So if there is any kind of pressure gradient driving the flow, for example, then this has to be there. And then here there is a term associated to like a simple model of viscous drag between fluid layers. And eta here is the viscosity coefficient. And this delta here, by the way, is a Laplacian. Sometimes people call that the vector Laplacian, just to say that if you write V in spherical coordinates or something, you need to take into account that the basis, the local basis of the spherical coordinates depends on theta and phi, whatever, and this is going to have an impact. Anyway, so this is just to tell you a little bit kind of the context here. Now, the kind of things I would like to describe is a situation where you've got a flow, what is called here a laminar flow. So I'm presuming a laminar flow, but it doesn't need to be. It's just easier to draw. You've got an obstacle here and you send basically onto it a particular flow. And a characteristic of that flow here is that when it's far away from the obstacle, it has a velocity u. That's the idea. And what you want to know is the obstacle size is L, the viscosity is eta, and you want to know then, in principle, you want to solve that problem. You want to solve the velocity field for that, and then you can relate velocity fields to forces and maybe know what are the forces exerted on that particular obstacle and so on. That's kind of the kind of things that people do on a daily basis in fluid dynamics engineering, okay? But here we just want to describe the equation. So if I simply look at the x velocities, that's the one that is the most affected by that obstacle, right? So you're going there, but then you need to pass through an obstacle, so the velocity Vx is going to be quite affected by it. It's going to go from u to some non-u and larger or bigger, I have no idea. And basically the equation that is satisfied by that field is this. I've imagined here that the obstacle is cylindrical, because then it avoids that I have to use a z component here. So it's just again for convenience and illustration. So let's see what happens. I've got this horrible equation, and what I want to do is dimensionalize stuff. So what I'm going to do first, and then things will unfold really from there, is basically introduce Vx tilde is equal to Vx over u, Vy tilde is equal to Vy over u, and then I'm going to introduce x tilde is equal to x over L, and then y tilde is equal to y over L. And what I want to see is how the equations already are going to change as I do that. So again, I want to substitute all Vx by Vx tilde. So if I do that, then this is what I'm going to get. So rho, then I'm going to get a u, and then I've got dVx tilde dt. So far, this is what I have on that side here. Then plus rho, then I've got here u Vy tilde, then divided by L, d, so that's u squared, dVx tilde dy tilde. I need to be careful here because it's easy to make mistakes. This is going to be the same for the other one, so rho u squared Vx divided by L, and then d Vx tilde dx tilde. So that's this term here. Then we have so far minus 1 over L dp dx tilde plus eta. Now we've got eta u divided by L squared, and then here we've got d Vx tilde dx tilde squared plus Vx tilde dy tilde squared. Okay, so this is the equation I have. Looks a bit more complicated just because I've expanded the terms here. But you see that I'm starting getting stuff that are all with dimensionless quantities. So for example, here I've got dimensionless, 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 dimensionless. This I'm not yet dimensionless, so I need to fix that problem. And the whole right-hand side here is dimensionless. So what I'm going to do is basically, this is surely dimensionless, so I'm going to divide the entire equation by this. Okay, so I'm going to get, and let's be careful here, rho u, and I need to divide by eta u, and then L squared, d v tilde x dt, then plus, so here I need to be super careful, so I'm going to actually put things together here, so rho u squared over L, and then here L squared over eta u, and then I put so that's a rho blah blah blah, and so here I can put things together. V tilde y dvx tilde dy tilde plus vx tilde dvx tilde, and then is equal to minus, so minus 1 over L, so L squared over L eta u dp dx tilde, and plus this term here. So I'm almost there. Here, what I notice is essentially that I'm going to get rho L squared eta, and if you actually check the dimensions, because this is completely dimensionless, so it does not depend on the physical dimensions of the system, it's only ratios of the typical length scales of your system, then that should be obviously the same everywhere else, because Navier-Stokes is a complete equation, so dimensional consistency is actually maintained throughout the equation. So what that means is that this has to be necessarily taken into account. So I'm going to introduce t tilde, which is equal, so basically this introduces a time scale. So t tilde is equal to it depends how you want to write it, but again, that's going to be t divided by rho L squared over eta. And if you check, actually, rho L squared over eta has a dimension of a time. So it's a typical time scale in your system for fluid flow to develop and so on. Okay? So that's kind of important. Basically, the only thing I'm going to introduce is P tilde, so dimensionless pressure, which is going to be equal to P over eta u over L. Okay? So basically, that's what I'm introducing. And the final one that I will introduce is basically what comes out of that stuff. So I'm going to say rho u square L squared divided by L eta u basically is going to be equal to rho u L divided by eta. And this is the only stuff that is going to remain in the equation, right? So everything else is going to be the differential operators as they were before, but then there is no prefactor anymore. Okay, that had a dimension, that had some unit, some value, whatever. Now these prefactors are not there anymore. I only have dimensionless quantities that I can put in a computer or whatever. And then everything else is actually put together into, or at least some aspects that are super important are put together into one final quantity that is going to be in the front of this convective term. And as this one, and this thing is denoted usually RE, and this is called the Reynolds number. Okay, so let's see what that gives. So in the end, what we are going to get is, for the equation, dvx tilde dt tilde plus, and then we've got the Reynolds number, and then times v tilde y plus vx dvx tilde dx tilde is equal to minus dp tilde dx tilde, and then plus vx tilde dx tilde squared plus vx tilde dy tilde squared. So if you actually look at what we've done, we've got one problem. This problem is a flow going through a particular obstacle or something that has a characteristic length scale, etc. Now, of course, there can be subtleties, a lot of subtleties in finding out which length scales matter, etc. Here it was slightly easy to understand that. But the bottom line here is that the equation we get, as you see, is going to comprise only terms that are completely independent of everything else. Okay, so it's these are scale-free equations, right? Because this term here is completely dimensionless. It does not depend on the units you're going to use. This term does not depend on the units you're going to use, and none of these terms are going to depend on the units used. They are simply ratios of characteristic variables with characteristic parameters, and that's it. Okay? So at the end of the day, if you solve, for example, these equations, then because they only involve ratios and stuff, then it doesn't matter whether the L, for example, is 2 centimeters or whether L is 10 centimeters or 10 meters for that matter, or 100 meters, because you only look at ratios of stuff. But what you see here, that everything is going to be governed in terms of the physics by that number here. Okay? So this number that is here is going to set everything. So if you set that number to 0.1, for example, then the physics you're going to get, whatever the real length scales and velocity scales and viscosity scales are, whatever they are in reality, if that number is 0.1 for combinations of that things, then the physics that comes out of this rescale variable is going to be identical. Okay? And that's what sets the law of similitude. If the Reynolds number is larger, then likewise the phenomenology is going to be identical, so basically again scale-free, insofar as you've chosen the right scales to look at. So it could be, again, like there could be problems, but that would come from maybe misidentifying the scales to begin with in your problem, which is a very difficult problem. So I'm not saying this is anyone's fault, but that's kind of where the problem may lie. And so usually the reason why people look at that number is because if the Reynolds number is very, very small, like let's say 0.001, then essentially it cancels out this so-called convective term. So that's a nonlinear term. And what is remaining is simply that is equal to that one side, right-hand side, which is a linear equation, which is called the Stokes equation, and which is much easier to solve. That implies the existence of laminar flow, so where the lines of the flow are not intersecting, they can't intersect each other, etc. And on the other hand, if this number is very, very large, then essentially part of these things here might be completely negligible. And so here, if that part is removed, then we get what is called the Euler fluid dynamics equation. And that gives rise to plenty of other stuff that we can discuss maybe later. But that's kind of the whole point. Everything is governed as far as this initial simple Navier-Stokes equation is concerned, with this Reynolds number essentially telling you which kind of fluid phenomena you're looking at depending on the value of the number. And then you can basically, again, simulate or model, like in real life, with simply smaller system sizes and different, you just need to tweak for example, imagine you find 0.1, and that's what you want to look at, 0.1, and you say, okay, I want to actually decrease the system size by 10. You say, okay, fine, I just need to increase rho by 10, and I'm done, right? And so you see, that's how it works. You simply need to make sure that this ratio has the same value, and you can basically decrease in size by simply increasing in density. If it's too difficult to increase in density, you may play on both the density and the viscosity, for example. Okay, so that's where the law of similitude actually comes from. So again, if you look, we have described things with. So now we've got 1, 2, 3, 4, 5, 6, 7. So we've got 7 variables, and before we had 7 variables, but then we had additionally we had eta. And then rho, and then u, for example. Okay, so we've got an L as well. So we have like plenty of additional variables that we managed to remove because of the independent dimensions that were involved. So we took care of the dimensional redundancy to express this in that particular form, which becomes scale-free, essentially. Okay, so that's it for today's video. If you've got any questions or comments, do let me know in the comment section. And otherwise, see you in the next video.